All right, I think we'll go ahead and get started. Good morning, and thank you for joining us for our webinar today as we take a look at collaborative electronic product development. Today, we have a great lineup of speakers to deliver our presentation. From UTEX Scientific, we're joined by James Seidenberg. From our partners at EM Works, we're joined by Adam Kibir and Ben Ahmed. And from CAD MicroSolutions, we're joined by Roman Dupak and Talal Asfar. We're going to be covering a lot of ground today with our speakers, so questions will likely pop up, which is great. Our speakers are all very happy to answer any questions that you may have during our Q&A period at the end of the session. So throughout today's presentation, feel free to type in any questions that you may have into the questions box in the GoToWebinar panel. If there's a particular speaker you're addressing your question to, you can feel free to include that as well. Today's webinar will be recorded and you'll receive the recording from us tomorrow. So if any questions arise after we wrap up here today, you can simply reply to that email and we'll put you in touch with the appropriate team members to get you those answers. All right, without further ado, I will pass things over to Roman to get us started.
Good morning, everyone, and I welcome all participants and viewers to our webinar. We're really excited that you're all able to join. And so, as you know, our webinar is called Collaborative Electronic Product Development, and we're going to be focusing on CAD design for PCB, as well as electrical schematic for 2D, 3D, and electromagnetic simulation tools. So our agenda for today's webinar will include an introduction. I'll give a very brief introduction of the industry trends and challenges, as well as the next follow-on presenter will be from CAD MicroSolutions, Talal. He's going to be presenting the electronic schematic 2D and 3D electrical and PC board design for manufacturing purposes. And then our guest, James from UTEX Scientific, will be providing an instrumentation case study showing how UTEX has used SOLIDWORKS Electrical. And then our final two presenters will be from EM Works, where they're going to be discussing typical challenges with antenna direction finding. So areas of focus will be high frequency simulation, as well as a showcase of a dipole array antenna. And our guest from HAYSYS, unfortunately, won't be able to join us, but on his behalf, Ben from EM Works will be presenting their customer case study using HFS high frequency simulation tool. And then we'll have our Q&A session for roughly 15 minutes. Our speakers, as Jessica had mentioned, I'll just quickly summarize again. From CAD Micro is Talal Asfar. He is our electrical engineer. Also, our guest from UTEX Scientific, James Seidenberg. He is our NDT Systems Design Coordinator. And then from EM Works, Adam Kibir will be joining us, our technical sales manager, their technical sales manager. And then on behalf of Joseph Hayden from HAYSYS, which unfortunately he has not been able to join us today, it will be presenting Ben Kusil from the application engineer from EM Works. And then as mentioned before, my name is Roman Dupak. I'm the National Strategic Business Manager for CAD Micro. So just a very brief explanation who CAD MicroSolutions is. We were established in 1984, all privately owned and Canadian owned and operated, headquartered in Toronto. And we have an additional 4 offices in the Waterloo, Cambridge area, specifically in Cambridge, and then another office in Montreal, another in Calgary, and New Westminster, close to Vancouver, BC. We're approaching 70 employees. And the key areas of innovative solutions that we provide is 3D printing, SOLIDWORKS design related tools, advanced simulation tools in engineering, and also VR, AR, and 3D metrology solutions. So just want to provide you a brief explanation of what are some of the key industry trends and accompanying challenges that we are moving forward with currently and easily within the foreseeable future. When I say foreseeable, I'm referring to at least 10 years into the future. So you've probably heard a lot in the mainstream dialogue about reducing our carbon footprint. So that requires a lot of technologies, green technologies, to facilitate that. One of the areas is reducing the amount of fossil fuels being consumed, either through the transportation machines that are being used, or also how electrical power is generated. And one of the ways to achieve that is there's a huge push in the development of portable nuclear electric power generation stations. So they're almost like quite portable. If you look at the picture on the right there, you notice the man standing It's quite portable, so it's relatively within the size of a building, much smaller compared to the current centralized nuclear power plants. So these are relatively the direction that we're going. Also, renewable energy, another renewable energy source that is being implemented is and developed are different types of electric power generating turbines. That is turbines from not just necessarily just wind, but turbines that are used installed within oceans or seabeds. So the waves of water are being used to rotate those turbines for electric power generation. And as we all know, solar panels as well. To facilitate the storage of some of these powers when power is needed, there's more advanced efforts being put into development of lighter and more cost-effective battery-dense power storage systems. In addition to that, there's also development of a lot of electric vehicles, and that is from individual electric vehicles to mass transit and ground rail systems that are necessarily not just electric, but are powered magnetically. Also, what's needed is to support these electric power generating stations and also these vehicle technologies, a lot more electric power is required. So more distribution is required, a larger distribution network is required, and transmission is required. So the expansion of these existing networks are required. So a huge demand will be required of copper, all your basic metal commodities. So copper will be required, more uranium will be required, more silver will be required, more lithium will be required. All the respective basic elements that require to support this infrastructure will be much higher demand. And therefore, this is where a lot more electric charging stations will be required. And if you look at the different pictures that are flowing from the top right to the left, you can see that we're going from portable nuclear power plants to panels to electric charging stations for individual vehicles and mass transit, as well as for rails and electrically powered individual motors you can see in the bottom left-hand corner there for an aircraft. All these technologies require significant CAD support, 2D, 3D CAD, but also even more advanced is engineering simulation tools. That's a huge involvement of a lot of these technologies have been developed and the continued development of these technologies and the implementation of them into our infrastructure. So just to finish off the trends and the challenges, another trend that's developing, as you all probably know, is 5G communication equipment. And that has to deal with a lot of our smartphones and the broadband data that's required to support autonomous vehicles, so individual vehicles, shuttles, and mass transit as well. If you'll notice on the picture there in the middle, there's actually a transit bus that was recently tested by New Flyer Industries in Connecticut, the first fully autonomous transit bus that was tested and is fully autonomous. So a lot of technologies are being done in development of that. Also, the trend that's happening is automation and manufacturing, so implementation of Industry 4.0, the particular area that we're focusing on in our business model. And so, a lot more automation and smart equipment that goes into the manufacturing floor. In addition to that, robotics and artificial intelligence. As you can see, the bottom right-hand picture there of a Boston Robotics robot that's jumping over a hurdle, and that's fully being done on its own through its own intelligence. And finally, also a lot of development and implementation of blockchain technologies. And I'm not necessarily talking about cryptocurrencies here. I'm actually talking about these same blockchain type of technologies are being used for transaction ledgers incorporated with AI decision-making capabilities. So what's being done heavily in the industry is Amazon, Walmart, all these large chains, even central banks are investigating how blockchain technologies can be used to streamline the process in going through their business and being able to monitor and refer any time of information that's being recorded. It's all decentralized, so information can never be lost. With the implementation of AI, it provides a lot of streamlined processes and cost savings that comes along with blockchain technologies. All of these are being investigated for the purpose of implementation in a very near future. And I'm talking about near future within the next couple of years, maybe even sooner. However, a lot of these technologies that we just discussed here, again, they're all supported by CAD tools, CAD software tools, as well as advanced simulation tools is a heavy important part of this. Without simulation tools, autonomous vehicles cannot be accomplished. because through advanced simulation, you're able to evaluate different safety scenarios whereby physical testing is absolutely impossible. It would take decades before automation systems can be implemented. And that brings us to the next presenter. And those are the industry trends. And so we will now talk about, as I mentioned, CAD tools that are used in the support of these industry trends, and then advanced simulation tools. So I'll pass on the baton now to Talal of CAD Micro. Talal?
Hello. Hi, Roman. Thank you very much for that great introduction. That makes my job much easier. So I'm going to jump in directly into this collaborative electronic product development. Roman touched upon the whole thing. I'm just going to focus briefly on the design side of it. So what you can see is there are different type of products in the market. It could be a small system like the robot we are seeing on the left side. That is one of our customers who's designing using SOLIDWORKS PCB. And the one on the right, which is a large system with PNID, mechanical engineering. And that is also a customer. So our customers range in, could be small product or large product, but something is common in there. And that is that there are different engineering systems which are being put together and different kind of groups who have to talk to each other to make this design viable. And the thrust right now is on 3D CAD because it's much cheaper to design your product in 3D than to do it really in actual prototype and keep testing and changing. So it's much cheaper to design it and also with the simulation actually test it in the virtual environment, right? So the main three engineering disciplines which come together in the design are the mechanical, electrical, and electronics. And I'm the electrical engineer. I'll focus on those two, electrical and electronics. There are speakers here who will touch upon the simulation aspects of it. So what do we design in electrical and electronics? A lot of different things, right? Power distribution could be motor controls, various kind of motors, pumps, etc. It could be PLC microcontrollers. Lots of machines use a lot of sensors. You need programming. That's why you need PCB. Nowadays, trend is in wireless data collection from the sensors or Internet of Things, or it could be completely remote operations, SCADA type system for virtual or remote operations of a system. So if you want to do that, what tools do you have at your disposal? SOLIDWORKS is starting to complete the whole picture by offering several products which work together. That's the most important part. They work together to offer you a complete solution. So on mechanical design, obviously SOLIDWORKS is a well-known product, right? So there are millions of users around the world. We also have a SOLIDWORKS electrical design software and SOLIDWORKS PCB software. And the most important part is that they complement each other and they work together to offer a complete solution. You individually, obviously, SOLIDWORKS Electrical is a separate product and SOLIDWORKS PCB is. But the real power comes when they start to talk to mechanical and they can transfer their information and system so that the three different disciplines I talked about, the mechanical engineer, which can include PNID people as well, and the electrical designers and the electronics designer all can come together to complete the product, and they can have a single platform to discuss so that there are no errors in the design, right? On that respect, I'm gonna keep my talk focused on two things: SOLIDWORKS Electrical. I'm just gonna briefly touch upon that. What is the power of that system? And I'm going to talk about electrical 3D, which is the connector between electrical and SOLIDWORKS. So going back one slide, you can see that there's a connection between the SOLIDWORKS electrical and SOLIDWORKS CAD in the middle. That is the electrical 3D. And you have a similar thing going on with the PCB. It's a design tool for PCB, but there's a connector between that and the mechanical. So the SOLIDWORKS CAD is the mothership where all the information is gathered together. At the end of these sessions, we'll have a question and answers. Please keep a tab of all the questions you want, note them down. And at the end of the webinar, I think there's a question and answer session. I'll be able to answer your questions. Okay, so let's talk about a basic electrical design. What happens there? Obviously, the electrical engineer is going to come down and do some kind of a schematic design. He's going to put his components on the page and connect them with wires and cables and all that, right? That's the definition of what electrical design schematic is. We call that 2D schematic design, mostly done in 2D by electrical engineers. But then he has to do a documentation process. And at this point, he might jump to another software, which is he has to create bill of materials, probably wire and cable list, from to list, etc., for technicians or engineers who are going to build the panels or the system, etc. So there's the schematic side, then you have the documentation, and then somebody actually has to keep an eye and do the audit. What does it mean? Well, the documentation and the schematic must match, right? I mean, you cannot have any error between the two. If you change one thing on the schematic, the documentation should show that, should exhibit all the changes. And somebody has to keep doing that because the design evolves over time and changes are made, engineering changes should accompany a documentation change, right? And that takes a lot of time. And what SOLIDWORKS Electrical does is actually it makes the design part easier, but even more importantly, it pretty much fully automates the audit and the documentation side of it. And that's where we save a lot of time. And in the automation part, we also include the electrical 3D, which it will bring all the information to the electrical 3D side and connect it to the mechanical side. Okay. It might seem a trivial thing to do, but if you look at, for example, just a simple example, this is a motor circuit, basic three-phase motor circuit, and you have a contactor relay to start to stop. If you made a change to this, what happens? Well, actually, there are a lot of changes that need to be made. There are 6 wires connecting to it, so you need to change power cabling, some kind of control wiring for start to stop, bill of materials, terminal diagrams, etc., etc. And before you know, you have to make like 30, 40, maybe 50 changes just by changing one component. And it's unbelievable that how many changes that needs to be done for changing even one component. And in projects, things need to be changed constantly. So what do you do with that? Well, if the system is keeping a track, in our system, it is done by an SQL database, which captures and stores all information automatically as you carry out the design, including all the wires, the cables, terminals, all kind of symbols you are putting on your design, all kind of manufacturer parts you are assigning to them, etc., etc. Once all of that is automatically captured, then the lower list is automated. To from list, terminal strip, bill of material, and customized reporting. Let me actually at this point switch over to the actual software and you will see this. So for example, let me show you this diagram. So this is kind of a schematic. This is what SOLIDWORKS Electrical looks like. And you have power and you have control diagram with PLC and system like that. But then you have terminal drawings, you have bill of materials, you have list of wires, and all of this is automated. You have about 15 documents, out of which I only had to create 2, which is the basic schematic design software of these 3 motors, which is the power and the control. That's it. And all the rest are automated. I just go into the report, and what this program is doing is keeping a list of all the cables automatically. It is keeping a list of all the bill of materials. It is keeping a connection list of all the wires, wire numbers, gauge, where to, where from, all that. All the symbols I put on my drawing are automatically tracked in this list. I don't create this component list, the software does, right? And that's the big power of SQL-based automation we are talking about. So it is keeping a list of everything. On that respect, then it comes to when you start to bring it, this is just a schematic design, we have something called 2D cabinet design or 2D machine design, in which you bring in the individual components and try to put them together and see if they're going to fit in a geometry, right? So that is the 2D schematic design. And this list of components is directly come from your list. You just put them together. And in that respect, if you want to go one step further, then you have electrical 3D assemblies, which you can generate. So within the software, we have 2D assemblies and 3D assemblies. And this is what I want to tell you about. The 3D is the mechanical software. So allow me to jump to the second software. And this might take a second. And this is the electrical 3D design, which is under the umbrella of, now I am in the SOLIDWORKS CAD 3D design. And this is some kind of brewery setup. You have 3 tanks with several sensors, temperature sensor, pressure sensor, etc. All this information is going through wiring to this electrical cabinet. And this whole thing is designed in electrical and sent the information to mechanical, where they incorporated it automatically under this. All this component list is coming from electrical side. How does it happen? Very, very simple. The moment you install the electrical 3D software, it adds in as a component here, and you end up getting this SOLIDWORKS Electrical 3D panel, which becomes a part of your design. And you just go into tool, and then you will see SOLIDWORKS Electrical. You open a project, you can view all the schematics. So this is not electrical software, but you can at least view all the schematics. You can change it on the electrical engineer. However, it's mechanical 3D, so you can open the 3D assembly part of it and insert all your components in 3D. And this is very valuable. Like if you are in the field and try to put components together, usually you have very limited time at the customer site to finish the work within 1 day or 2 days. You cannot make mistakes in wiring. This allows you to check what is going on. Like this red wire will go from this component all the way up into this component. You can keep a track, makes it much more visual and easier. Before you even ship it to the customer site, you can see the size, how much, what is required from here, what will be the path of your electrical wiring, how it will be routed, etc., etc. Right? You get the drift of what we are doing here. So coming back to our talk, because of this SQL-based database system and combination with electrical 3D, we have much faster schematic creation, we have rapid change management, and then you have integration with electrical and mechanical, right? Now, moving on into the same information system, there is SOLIDWORKS PCB. That's a separate software. And on the PCB side, which is the electronics PCB, you have your own challenges in the modern system design, which is, you want to have electrical and mechanical software integration because just like I talked about that robot here and the PCB side, and we are going to come to this example, you have a mechanical design, but then you are also trying to do the electrical design, electronics. You will have very complex board shapes, very constricted spaces, and high precision component placement. It's easier if I show you how this works. Also, let's talk about this robot, for example. In this robot assembly, which is done, we are in mechanical side. You see that there is a battery on top, and then this small compartment contains your PCB, okay? And as you can see that there is a very small space it has to fit in. There are lots of components in there. There are some fingers going into the battery. We'll come back to that. If we open the second compartment, we will see that the shape of the PCB is not rectangular. It's a strange kind of shape. It has to fit according to the mechanical design. So the challenge is now mechanical engineers are going to design their system. Now you need clearance, front and back side. For example, if you measure here, this backside connector to that metal plate down, how much is about 0.5 millimeter, right? That's high precision that you need. So you need to have a 3D environment to understand how your components are going to fit in there. For example, the battery is there. Now, if you have a connector on the PCB board which has to get the charge from it, so those fingers need to go inside the battery. What kind of precision are we talking about here? So again, let's go ahead and measure a little bit between one side of the battery and one side of this connector, and 1/4 of a millimeter. when we're talking high precision, we are talking sub-millimeter kind of precision, which is required in modern PCB design. How do you do that? Well, the thing is we have the connector between SOLIDWORKS PCB and SOLIDWORKS Mechanical. That allows us to send the whole PCB board into the mechanical design. And once we send it, the mechanical engineers and electrical engineers can work together to change the design of the board shape, and that allows for complex board shapes. And then we can also use very advanced design features in the 3D CAD software. Now, the PCB softwares usually typically don't have very precise control over things, but in mechanical design, everything is down to micro, millimeter, sub-millimeter is easy for them. So it already has built-in features which we can then use. So these two start to work together. There's an intermediate process where you send the design to SOLIDWORKS PCB services. It could be anywhere in the world on a server. And then the next day mechanical engineer comes and he can take that. And let's see how it works. Let's say you have your schematic done. This is the SOLIDWORKS PCB side, and we are just creating a new PCB board and saving it. And this board is typical, just this blank, square, rectangular. Now on the right side, I have this little tab. I just click one thing and I'm pushing the board. There are just two buttons. It's very simple. I'm pushing the board to the server, to the PCB services, towards the mechanical, and that's it. The board and all the information has been sent over there. Now I can switch to the mechanical side. On the mechanical side, I have my robot assembly. Again, I have this push-pull, couple of buttons in there. I log into that server, that PCB services server. And then in that server, I will see a complete list of projects. And then from there, I can see, okay, what is my project? I can, select which project I need the board from and just say, okay, and it will pull the board out, right? And it is pulling the board out. It was a square shape. I bring the board in. Notice that I didn't do any file conversion. It automatically converted the SOLIDWORKS PCB file into an SLD part, which is a SOLIDWORKS native format. So it is an automatic conversion of two different file formats for me just by a click of a matter. Now I bring that board, put this, what is called mating in SOLIDWORKS, which is the 3D control of how I'm going to arrange things. This is a very, very powerful feature in SOLIDWORKS, which I am using to my advantage in here. So now I want to change the board shape. Again, I have lots of different options available in here. There's something called the context of the component features. Now here, this is the board part outline, and that comes with a sketch. The whole outline is contained in this square sketch. I'm going to change that. I don't need the rectangular one, so let's delete that. And I need a complicated feature. So that's called convert entities. I'm just using that and using a more complicated sketch, which is much easier to do here. It's no problem in doing in the CAD environment, and just use that as my board outline. And that includes how it's going to fit. I can see the mechanical components behind it. So I can design it in the mechanical environment, seeing how it is going to fit in the 3D, right? And once I'm done with it, I'm going to save this file and send it back to the PCB side. And again, that process is going to be very simple. This is just, this is the new shape of the board. And again, I'm going to save this part and go to my here and just push it to the PCB and give them a note like, okay, I've changed the board shape, whatever you want to send to the thing. Now it could be mechanical engineers and electrical engineers talking to each other, or the electrical engineers doing both things at the same time. Both are possible. It's easy to do, very, very simple. Now on the PCB side, I check there are changes, view changes. I say, okay, what kind of changes? I'll accept them. And I see that the board shape has changed, right? So that is one thing very easily done. You can see within 5 minutes, I had a complicated board shape transferred, which I couldn't do in the software. And this is based on LTM, one of the best engines. Now, for example, you want to place a component. We talked about 3D placement, very high precision requirements. So how do we do that? So let's say we start with one simple connector. This is the one which is supposed to go with the batteries, with the fingers in it, right? So this is how you place components in typical NEPCB software. Like you will rotate it, you will place it. You can arrange the coordinate a little bit, but you don't know the precision. You are working in dark because you don't know where the battery is going to fit, how the mechanical is going to fit. Here, what I'm doing again is I'm just placing my component, sending over to my, let's say, mechanical department or anybody else who is going to deal with that. Send it over. And again, on this side, the change has come. It's the same board they were designing. And they are going to accept those changes. And here we go. We have that connector in 3D. Okay, and we can put it on the front or the back. Now, let's say we bring that part in and try to arrange. You can move this whole thing around a little bit so that it is placed right in there. And we are going to use again that advanced mating feature to central. So that is very, very easy to do in 3D CAD because they have built-in advanced features like the width constraint and that constraint. And we are going to use that to our advantage here to find the exact spot this connector is supposed to be in regards to the mechanical and the board. And that's it. It was just a one button thing and it is arranged. So as you can see, you can have complicated board shapes, very complex placement of components, much easier done by this back and forth, which is almost seamless. So what I will say in conclusion is that we have a seamless integration of SOLIDWORKS and electrical design. And by electrical design, I mean both electrical schematics, power system, as well as PCB. And what is very powerful is this automatic file conversion and transfer. You just do one click of a button and things are transferred. There's no messy third-party software which needs to integrate with them. All is under SOLIDWORKS umbrella and still one homogeneous place where all the software works in tandem with each other. Okay, thank you for your attention. I will conclude at this point and I will hand over to UTEX, and they are actually using SOLIDWORKS for their design. So James, if you want to take over.
Thank you, and good morning, everyone. My name is James Seidenberg, and I am a systems designer at UTEX Scientific. Today, I'll be discussing what we do and how SOLIDWORKS Electrical fits into our design process. But before I can explain what UTEX does and how we use SOLIDWORKS Electrical, I first need to quickly explain the core of our business, non-destructive testing. For those unfamiliar with the term, non-destructive testing, or NDT, uses various methods and techniques to non-invasively determine the integrity of a material. In contrast to destructive testing, NDT is done without doing any harm to the part, allowing it to be used in production. NDT plays a critical role for many industries to ensure safety, reliability, and also cost-effectiveness. Our clients come from many critical industries where safety is of the utmost importance. Some inspection systems we create deal with nuclear fuel tubes, jet turbine blades, windmill ball bearings, and even spacecraft components, just to name a few. UTEX has dealt with almost every type of NDT technique, but we specialize in ultrasonic inspections. To give a quick idea as to why our systems look like they do, it's important to have an understanding of how the technique works. It is the same basic principle as an ultrasound for a human, but it's for materials and is performed quite differently. When sound waves hit a boundary, the sound will bounce off and change direction. Some energy may reflect back to the sound source, in our case a probe, and some will scatter. In this picture here, you can see our probe, which both transmits and receives the ultrasonic sound waves. When inspecting a part, you get a baseline signal based off of a standard. When the sound meets an indication in the part, the ultrasonic waves are no longer going to return to the probe, but scatter, reducing the signal we see on screen. Depending on the size of the indication, the part will either be accepted or rejected. Because sound is a mechanical wave, it requires a medium in which to travel through. Air is actually a poor medium for ultrasonic waves, so a couplant is required, the most common being water. This means our systems typically consist of a motorized gantry system over a large tank of water. However, in some cases where parts can't be fully immersed, a squirter system is used where a jet of water is sprayed at the part, and the sound is sent and received through that water stream. UTEX designs and develops software and instrumentation for building NDT systems. We develop InspectionWare, the industry standard for building applications for all types of NDT. It is not simply a program, but the platform which NDT software products are built. We produce the UT340 ultrasonic pulsar receiver, the worldwide standard for both ultrasonic research and industrial applications. We retrofit older scanners to give them more modern capabilities, and we also design and build brand new systems for clients. I am involved with every aspect of a system build, from the design of mechanical and electrical systems, software development, and the building of the scanner itself. So where does SOLIDWORKS come into play? We do not have a standard system that we sell. As mentioned earlier, there is a broad range of applications for NDT, and almost every customer has a unique requirement for their testing criteria. A titanium billet scanner is going to look quite different to one that scans ball bearings. We are constantly designing new systems, and with that comes the requirement for new and unique schematics. Prior to my employment at UTEX, our electrical engineer would use DraftSite. This produced simple but dumb schematics. It was very easy for errors to occur and not to be found or corrected. The circuitry was sound, but things like components being labeled incorrectly, labels not updating throughout the schematic, or wire labels being in weird positions were constant sources of frustration. Our panel builders would have difficulties with these schematics, requiring back and forth for clarification, or even having to do rework, costing us time and money. SOLIDWORKS had already been chosen to be our CAD system of choice for all of our mechanical drawings, but with UTEX being a small company, we didn't have the time or manpower to learn SOLIDWORKS Electrical until I joined the team. There were a few things that drew us to SOLIDWORKS Electrical. First, the integration between SOLIDWORKS Mechanical and SOLIDWORKS Electrical. We wanted to have a complete model of our system. You will have seen earlier in Talal's slides that you can model your cabinet and have everything there, including cables and wires. We can have a model of not only the tank and electrical cabinet, but the cables going from the tank to the electrical cabinet, as well as the wiring within. We would be able to see how certain power and signal lines could be routed and optimize these routes to ensure the lowest amount of electrical noise possible. We need very low noise systems due to the nature of our inspections. Too much noise and defects can be missed. That is obviously not a good thing. Routing also gave us a very good approximation of wire and cable lengths. This helps us not only with ordering, but if something needed to be replaced, what exactly would be required. Another important aspect of it is it allowed us to create complete electrical schematics. And by this, I mean that every single part of the electrical system can be included and represented accurately. For instance, some may argue that you do not need to label each individual terminal on a terminal block. This may be the case in some scenarios, but for us, it has changed the way we are able to get our panels built and how we troubleshoot with clients. Our panel builders have told us that we are providing the best schematics that they have ever worked with. They are complete and consistent with very little, if any, errors. This has reduced the amount of rework required, saving us time and money. Troubleshooting has also become much easier. We can track down issues quicker and easier with these schematics. Much of our troubleshooting is done remotely over the phone. Many of these systems go into restricted areas, so once it's in place, there often isn't any internet access or the ability to take photos or videos. If something is going wrong, our client can describe their issue and we can tell them exactly where to look based off of the schematics. Furthermore, many of the people running these systems don't necessarily have a lot of electrical experience. So once we walk them through how to safety the system, we can direct them to the exact location of where we expect to see the issue. Did something happen recently with the system? Was it moved? Did a component get damaged or did a wire get tugged loose? We can tell the clients exactly where to look so they don't waste any time hunting. You got to check terminal block 53, block 1, position 2, which should have a blue wire that is numbered 302. Did that wire come loose? Is that wire even there? If not, why isn't it? Because we didn't do it. So our troubleshooting proficiency has increased dramatically. One of the most important aspects of electrical to us, though, is the interconnectedness of the entire schematic. It is amazing how there are relationships between manufacturer parts, symbols, wires, and connection points throughout the entire schematic, which mirror how they are on the physical system. A simple example of automatic updating is to use a relay, similar to what Talal already showed you. There are typically two parts to a relay, the coil and the contact. These can be represented by two completely different symbols and can be located in different parts of the schematic. Once we associate the symbol as the same component, we really don't ever have to worry about whether those parts will remain connected. We can change things like the component tag number or even change the part completely on one symbol, and everything will be updated accordingly without any manual intervention. When symbols are made correctly, it also allows terminal numbers to be updated correctly. Let's say the original relay had a normally open contact that was 11 and 14, but the new part had its contact as 43 and 44. The symbol will update with this information without me doing anything. Automatic updates also allows for quick changing of multiple symbols. For example, you need to go from an ANSI to an IEC drawing, or update the colors of all your wires. It really speeds up the process of making the schematics. Macros have also really sped up the schematic creation. While a lot of our cabinets will be different in layout and number of components, certain circuitry is used in almost every system we build. For instance, here are two different power supplies. Once a macro is created, I can simply drag that macro onto the schematic and it's done. If I need to change anything, it's as simple as right-clicking and changing the properties. Finally, generating reports, such as bill of materials, is easy, complete, and customizable to suit our needs. These used to be done by hand, but now with electrical, we can export a bill of materials, import it into our internal database, and have the parts records associated with the new system. This allows purchasing to see whether there are any parts we haven't used before. If we have used the part, do we keep any in stock? And if not, where did we order it from last time? SOLIDWORKS Electrical has come a long way since I first started using it. It hasn't always been smooth sailing. However, with my help, the help of CAD Micro, and the SOLIDWORKS team, the latest version of Electrical, 2021, has shown to be a solid application and an impressive update. Electrical is adaptable. There will generally always be some work that you need to put into it, whether that is recreating some parts, some title blocks, or symbols, but some institutions may be able to do minimum work and have it working more or less out of the box. Others, like mine, have required quite a bit of work to get it to the point where we are happy with the results, matching standards that we used prior to starting with electrical. There certainly is a learning curve, and figuring out how to use the tools effectively is a must. I'm not going to sugarcoat it. Previous versions of electrical had been buggy and slow, which did cause a lot of headaches. But I do believe that if I had started with 2021, the amount of time it would have taken me to set things up would have been greatly reduced. Overall, SOLIDWORKS Electrical has been a great tool for us, and we do look forward to using it as it continues to grow and improve.
Well, thank you, James. Thank you, James. Thank you so much. Let me now take the screen and just kind of complete the picture of what both James and Jafar spoke about. And how do we complete the picture? We're going to basically be speaking about two main products that we offer at Electromagnetic Inc. or EM Works Inc. And while what Jafar and James spoke about or presented is the CAD part, is the 3D CAD part that SOLIDWORKS offers, we actually go into a deeper angle of analyzing and connecting to the photo industry by filling in what is called the simulation part and providing a solution for the electromagnetic simulation, a full 3D and a 2D electromagnetic simulation. Now, as you all know, SOLIDWORKS has some simulation products like CFD flow, mechanical, structural simulation, as well as plastic simulation. But the part that's missing to really provide the photo industry users and the needs of nowadays industry is a magnetic and electromagnetic simulation, with us going into the picture and filling up the square of the puzzle. We provide together with SOLIDWORKS a full multi-physics solution for customers and for users. Both of our products at EM Works Inc. are Gold certified products, and probably Roman, James, and Jafar would know, are more familiar with that. What Gold certified means, not only our solution is integrated inside SOLIDWORKS, but also it has a tight integration wherein the user interface, the toolbar, the documentation, all of that have the same look as that of SOLIDWORKS. So this really helps a lot the learning curve. So if you happen to be skilled at using SOLIDWORKS, look no further our software looks very similar, and you'll be able to learn it quick. Now, as both Roman and Jafar and James presented to you some different sectors of industry that are the challenge of nowadays, and those, a lot of what they spoke about, really part of it has to be solved electromagnetically and simulated in order to be able to look at things that the normal eye or the normal testing, the normal prototyping does not provide. And for example, if we look into try to analyze a motor or a solenoid, or you try to analyze a loudspeaker or an actuator or a switch relay or any kind of inductive charging, or there are wire transfer and so on. But when you do the actual testing and prototyping, you don't see the charging being transferred from one coil to another. Well, our solution can enable you to see exactly what's happening and look at the magnetic fields and plot different results, so you can dissect your model, whatever you're making, your magnetic clash or your motor, electrical motor. And we all know that electrical motors is really a big thing nowadays. Or if you want to look at the radiation of your antenna, those things cannot be seen in normal testing. So the software can enable you to see these nitty-gritty details and hence be up to speed with what's going on nowadays. Now, if we look into one of the sector that's really important and we spoke about is the electrical motors. We all know that reliance on fuel and traditional sources of energy is decaying, is getting older and older by the days because of the environment issues, as Roman said, because of the safety, the future of mankind and Earth. There is a tendency to go towards electrical motors. So our software EMS can help you fully build your motor inside SOLIDWORKS and do your electrical simulation or electromagnetic simulation using EMS. With us, with our software EMS, you can compute the performance of your motor. You can vary the windings in your motor, work about ways of how to reduce the weight in your motor by doing multiple design scenarios and re-simulating and leapfrogging and relooking until you come up with the ultimate design, and you'll be really up to speed and abreast with what's happening. And, electrical motors are used not only in cars. Electrical cars is really is not something of unusual to see in the streets nowadays. Actually, there is talk, and we have seen some prototypes of small electrical airplanes. But I also know that in California and some other parts of the world that they use, trucks for dump waste trucks, these fully electrical buses, fully electrical, and so on. So really, us at EM Works Inc., we believe in the power of electrical motor. That's why we have a solution for electrical motors. So with us, you will have a solid solution. And look at this motor, for example. Imagine building this motor and testing it, in the lab and so on. How much work is going to take and how many materials is going to take and so on. Well, with this simulation, you can see all that, dissect what's inside your motor, look at it. Yeah, there is something wrong there. Yeah, it's turning well. Yeah, this is the torque I want. This is the size I want. Shall I reduce it a little bit? Yes, I can reduce on this side a little bit and here on this side. Then rerun and see what the simulation gives. Well, it's a lot of challenges, and we try to really narrow the gap on the challenges. And really, our aim is to save the user time and money. That's essential. That's part of what's happening nowadays. Technology means saving time and money. That's what technology is. One other area is power, the electronics. Well, there are, of course, transformers is very wide. It's a very complicated and highly demanded, transformers, because an electrical power, in order to provide electrical power or produce an electrical power, you need to have some sort of current. And imagine if you want to go from a high power electrical power that's going to carry electricity to your house or to your enterprise, at your company. Well, it goes in thousands of orders of voltages. But how are you going to go from there to your computer, to your refrigerator, to your TV. Okay, how are you going to make it 110 volt and so on? You have to have a transformer. A transformer accepts a massive number of current, and you're going to reduce it to small units of current. There is heat, there is safety, there's a lot of things. But again, you can all build that inside EMS, analyze it, dissect it, look at the magnetic fields, look at what you're going to get, how the transformer is going to behave. Is it going to overheat? Is it going to explode on me? So is it going to hurt my house, my environment, my company? How to build a safe transformer that's capable? How can you really visualize the capacitance, the inductance of your transformer? All these design scenarios can readily be done inside our product EMS. And while EMS really kind of covers the industry where electrical power and so on are of electrical motors are channels, but what if your motor, your car, the self-driving car you make, your phone you're talking to, okay, how you going to make them cooperate with the outside world, with people that are not next to each other, with companies, with other utilities, and so on, okay? You're going to need what is called a powerful antenna. Hence, with the antennas, you're going to be really, you're going to plunge in the high-tech part of electromagnetics, wherein our product, HFWorks, comes in to really help you be top of the high tech companies. So, for example, if we look at Google phones, if we look at Apple phones, if we look at Samsung, well, every phone does have two antennas at least. A Bluetooth antenna right here. I'm sorry, a GPS antenna right here, and Bluetooth antenna, and a Wi-Fi. So how are you going to connect with the outside world? You're going to have plenty of antennas. Nobody knows how many antennas. I mean, maybe you guys are talking on the phone every day, but don't know how does it communicate, but you need that phone. But how you're going to build that phone that's going to work well on that, the antenna that's going to work well in that phone. How are you going to build an antenna that's going to work well in a self-driving car? Okay, so you have an electrical motor, that's great, okay? Doesn't make any noise, it's good for the environment, but how is this car is going to drive by itself? It has to have sensors, has to have antenna that can see and analyze the info and be able to direct the the car as it goes down the road. You need also a GPS antenna. And actually, the next, presenter will be my colleague, Mr. Cookie, and he's going to speak to us about a dipole array antenna that's used in GPS. So that is also part and parcel of the same, challenges of nowadays. How to make things communicate easier, faster, and yet more powerfully. One other area is the RF components that we see in, for example, biomedical devices, MRIs, that we see in different applications. Like if you go into the airport, you're going to have to check your luggage checked. It goes through a scanner, or that scanner uses some RF component that's going to really send the way and be able to understand if you have, if you're good to go or not. Really look without having to open inside your bag and look. So it's really, if one look at it with what SOLIDWORKS builds and what we analyze and what the electrical provides and so on, all put our hands together, join our hands together to give the end user the tools needed to be up to speed of what's happening nowadays and be abreast and maybe even ahead. This is some names of our customers out there. Believe it or not, did not have, I know that Facebook is using our software for designing motors, but as all these names here, that probably you guys know about them. Ford with electrical motors, American Standards, Siemens, Raytheon, those are really L3 communications for HFWorks, Magnet Shoes for using, they use our software for designing all kind of lifting machines, and they also make a lot of solenoids, actuators to push, move, close, open, and so on. So it's Garmin, it's use our software. Garmin, we all know it's a GPS software, so you have to have dipole array antennas there or some sort of an antenna, a GPS antenna, and all that is done with our products. And we help these companies to be really competitive enough. They've been customers for years. They still are. They're happy with the solution, and they truly believe that it is saving them a lot of time and energy, because some applications can be very intricate, very complex. I would like to mention that if you guys need some particular info about our HFWorks product and EMS for low frequency, our website would be a good way to go. You can contact me straight on that adam@emworks.com or on my phone number there, but our website will be the best way to go. From there, you can click contact and move forward. And now let me pass the screen to my colleague, and he's gonna try to present to us an antenna, how it is analyzed inside HFWorks. Is what I've been presenting is fine and dandy, but let's see in reality how is that done. So here we go.
So good morning, everybody, and thank you for joining. So I'll just pick up where Adam left off. So I have a short presentation really about what I'm going to show you today. This is going to be an illustration of capabilities and the workflow. How do you actually get stuff done inside SolidWorks for high frequency simulation? So my first, really very quickly to pick up on what Adam was mentioning, really our products are about simulation driven product design and development. And when you talk about simulation, there are different types of simulations. There is circuit simulation, circuit-based simulation, model-based simulation, and there is field-based simulation. And we are in the field-based simulation. And so why do you need field-based simulation? Is circuit simulation is limited. It's as accurate as the models you fit into it. What's a resistor, what's an inductor, and so on. In the circuit setting, you really don't know the physics behind. So if you want to get accuracy, precision, and avoid unnecessary trial runs and testing, excessive testing, and so on, you shouldn't work with models. You should work with physics. Circuit simulation is not even feasible in certain cases. What's a circuit representation of an antenna? It doesn't have a circuit. You have to solve or some optical devices and so on. So field-based simulation is essentially the key here, because it's designed from basic principles. We solve the physics of the problem. We go to Maxwell's equations. And EMS and HFWorks are both field solvers. And today I want to talk to you a little bit about HFWorks, which is one of our flagship products. And again, in this context, you see the importance of simulation is that this really gets you there much quicker with a lot more reliability. Okay, and you don't need to prototype your design. The simulation, when the simulation is accurate, you basically can go from your simulation to prototyping and fabrication in one shot. And HFWorks is really an integration. It's an add-in that gets on top of SolidWorks, and it's a code certified add-in. Okay, and we leverage all the capabilities that SolidWorks does offer in terms of geometry handling, all of these features, the multi-configurations, the parameterization, all mechanical details of a design can be there and so on, and we can leverage that. So I would like to give you a flavor of this by talking briefly about this the antenna need. So today I think connected objects and the Internet of Things and so on is happening thanks in large part to the wireless technology, but there would not be a wireless technology without antennas. So the need for antennas is increasing and is touching essentially all aspects of our lives, and that's why we wanted to illustrate an example of an antenna, although HFWorks is capable of handling a whole host of other applications, such as microwave components, filters, dividers, couplers, and so on. You can do electrothermal, you can do microwave heating, RF heating, you can do antennas, radars, resonators, a whole bunch of things. But for the sake of giving you a quick introduction and the flavor, I wanted to focus on the antennas because of their importance. So today, I want to consider this a simple example. The kinds of antennas you can simulate are only limited by your imagination and your ability to capture them inside SolidWorks. So anything you can draw and that has an antenna behavior, expect to have an antenna behavior, you can simulate, you can characterize in the software in HFWorks. Okay, and then you can go after and look at key antenna parameters, and that's what I would like to show you next. Okay, how do you get this done? And I'm going to show you this model inside SolidWorks, and very briefly, again, because we are limited on time, give you a flavor of how that is done inside SolidWorks. Okay, so the goal is really to go after and see these kinds of results. Okay, and to do that, I would like to maybe tab over to my SolidWorks here. So the idea, again, the integration, to start with, this is your classical conventional SolidWorks. You build your assembly. This is my antenna assembly, you can see. And once that design is set and is done and is ready, you see the HFWorks show up as an add-in here. So it's a tab, okay? And whenever you're ready, you'd go here, you see your assembly. You could just go and do simulations. If you're familiar with SolidWorks simulations for mechanical, it's a very similar approach. A study is a simulation. There are different types. You can be doing antennas, you can be doing a number of these different studies. And when you do a study like an antenna, basically you'll need to specify what kind of frequency, maybe some general setting. You want to do parameterization, you want to do only look at the ports, are your impedances correct at the ports, and so on. Then you can control the frequency, which you do. You can do frequency sweeps of different kinds, and so on. We give you quite a bit of control over meshing, how you do the meshing. You can do it adaptive and make it do its thing. If you have some expertise and you want to control the mesh, you can do manual. You can hybridize those two. You can do coupling to thermal, so you can see heating effects and so on. And also there is an interesting feature that if you're worried about high power application, if there's going to be arcing or breakdown somewhere in your model, you can have this feature that you can use here. So when you say okay, it's essentially what it does, essentially creates a study structure. Okay, you can see here, and it's showing me all the parts that I have in the model, and these are labeled materials. Okay, so it's telling you that we need to define these materials. Okay, and then we need to define some boundary conditions and excitations, and we need to have a mesh. Those are really the three very simple, very basic steps. And you've seen in the study definition that this is SolidWorks compliant. So you're using the same process. It's as if you're executing a SolidWorks command. So you would apply materials, you would do boundary conditions, you would generate a mesh, and then you would solve the problem. Okay. I don't have, I believe, enough time to walk you through these steps. So let me go back to this study, which is already set up. So I can show you here. You see that I have a check mark. It's green. So all my materials are applied. So I have air, okay, and have some metals around here, and most of it is air, and these are metallic parts. Okay. So that's why I'm modeling all of them as perfect conductors. I can model them as copper or aluminum or whatever the structure is made of. The next thing we have is boundary conditions. So this structure has multiple ports, okay, that I number differently. And I have a radiation box. So if you notice, I'm not showing the air box around this, okay, but because when we do simulation of an antenna, we're truncating open space. So when we truncate open space, we need at the outer boundary of that open space, we need to apply a specific boundary condition. We call it a radiation boundary condition, which says the fields from then on are going into space. Okay, and so these are the boundary conditions and the excitations that we set. We did some meshing. We can apply mesh controls, so we can control the mesh locally. So these are dipoles. So each dipole here is center fed. So I have a port here, and this gray structure is just the mechanical structures that's holding the array together. Okay, and basically I've controlled the meshing and so on. Again, for time purposes, I'm not going to go into there. I just want to take a couple of minutes to show you what happens. So when you look at this study, which doesn't have results, it hasn't been set up and solved. This one has been set up and solved. The main difference is that we have this results folder now. And in the results folder, you have this circuit parameters, and we have different ways of looking at circuit. I mean, you can look at tabular format. So you can look at, we did the simulation from 2.3 to 3.3 gigahertz, and we have 6 ports here. So I actually 5 ports, and we can look at different frequencies. What is my S matrix? What are my port impedances? I can look at the different input ports of this thing. I can look at VSWR at different frequencies, at the different ports, which port is matched, which not. But that's the tabular data. Usually what we want is to have some kind of plot. So you can do 2D plots, you can do Smith chart plots, and so on. So I look at the return loss of different ports, for example. And we can see here that this structure is relatively well matched, and we see that two of the ports are actually behaving slightly different from the others. So they have a little bit better matching. And if we look at that and we look at the model again, here we see that these two ports are not symmetric compared to the others. So these two ports are actually separated by this kind of metallic rod that's holding the whole structure, and that's showing up in those two ports have slightly different impedance matching profile. So you can do that, of course, if you're more comfortable with VSWR plots, you can plot those as well, and you can look at these and play with them the way you like. You can, within this 2D plot, I can very easily quickly look at the data as well. So I can go at tabular and look at my data to examine precisely what's happening for my design. Okay. Now, these are basically the kind of circuit type parameters of an antenna. It's basically the input impedance, the matching, and so on. But what's really more interesting for antennas is the radiation pattern. And this is what we do is we have a whole folder of results for radiation, antenna parameters we call. And here we can do all kinds of calculations. Every time we want to produce a pattern or whatever, we create what we call a far field case. So here I have a far field case where all antennas are excited. If I say edit definition of this one, so you can see what we did. So we had these ports all excited, same power level, same phase. And I said, okay, discretize the far field in this, 2 degrees, and theta I wanted to have a more resolution in theta, less in phi. And then I can look at what is that giving me. So this is now the interesting part of the work, is to look at what the antenna pattern is going to look like. So first I have the antenna parameters table. So here I can say, the results of my antenna simulation. And here in this section, I have the gain pattern. This is really what we want to look at, is how is this antenna radiating? Where is the gain? Where is the field concentrated? So actually, this is the field I wanted to show. This is the field, the gain pattern. So I can take cuts of the radiation pattern in different planes. Okay, and in this case, I'm looking at my radiation pattern for the two scenarios. So I did excite all of them in phase, and excited all of them with progressive phase shift of 72 degrees. Okay, so the red one with blue dots is everything is in phase, and the kind of brown without symbols is when I have a progressive phase shift. Okay, and again I can just go around and see what do I have in terms of gain at different angles, okay, and for different scenarios. Okay, so this is a very brief. I hope I stayed in time, for this one. And obviously, you can also do other things. Look at the electric field and the magnetic field distribution and so on throughout this design. So with that, I want to go back to my presentation and close. But I think that if I hope I was able to convince you that and show you that we have a useful tool, a powerful tool for characterizing antennas and finding gain and obtaining the gain and the antenna parameters for an array, or it could be a single element and so on. So we can play with this, investigate the radiation characteristics of the array easily. You can do this even in the presence of other obstacles. So if you wanted to put something around your antenna, if there is an obstacle or there is a metallic object close by, you can see how that affects the radiation and so on. And I think one of the useful features, we make meshing very, very easy by having these two options, one for manual and one for adaptive. And with that, I want to hand it back to Adam, and I'll be happy to answer any questions.
Thank you, Ammar. I think Jessica will take over from here.
Yeah, that was excellent. Thank you very much to all of our presenters. As promised, we do have some time left to take any questions that you may have. So if you haven't gotten them into the questions box yet, you can still go ahead and type them in there. We do have some in the queue, so I think we'll go ahead and get started. So the first question that we have here is directed towards James. The question is, what do you think are the most important improvements in SOLIDWORKS Electrical 2021 over previous versions?
Well, I think the biggest improvement has been speed. In previous versions, for instance, if you were doing an origin and destination arrow, At times, depending on the size of the schematic, one origin and destination arrow could take upwards to a minute. That is not ideal when you do have a large schematic and you're doing a lot of connections. We tested out different bugs. Like I said, I worked with Talal a lot and SOLIDWORKS, and even across computers and different versions that kind of stayed the same. But with 2021, it's no longer there, and everything is very fast, very snappy. But for me personally, one of the biggest improvements was the fact that you can now move a wire and have it retain its properties. So for instance, if I had a wire going from one relay to a terminal block, but I wanted to change the position on the terminal block, as soon as I moved one end of the wire on the terminal block and wanted to move it somewhere else, all my information used to be deleted essentially, and I'd have to redo everything. Now there's a check mark in the configurations where you can actually retain all that information when you move one end of a wire. So that is huge for us. Like I said, the speed was the biggest thing as well. It just makes life a lot easier and a lot faster, obviously.
Awesome. That's great. Thank you, James. Next question I think is directed towards you, Talal. The question here is, are there project and page templates available in the SOLIDWORKS Electrical libraries?
Yes, absolutely. They are available. I don't know if I can show my screen or not. There is a setting in, of course, it's a complicated software, so you have lots of settings. So we have a very simple way of retaining all your settings. That is, you create a template. So first time when you start, obviously you have to set up your environment and everything. But once you are done, you make something called project template, which even includes all the title blocks, etc. And you can just save it. It's something like macro, but it even more advances. The whole project setting can be set up and just placed in one place. And for that company, then you can keep on using that template. You don't need to come in the morning and do all the settings again. Everything is ready for you to go. So you can customize it. There's a great degree of customization with every software. That's the concern. You have different users who have different requirements. So you want to give them both an option to customize, but then it makes it more complicated, obviously. So you want to have such templates ready to go so that everybody is happy with that. So I hope that answers.
Great. Thank you, Talal. The next question that we have here is directed to Dr. Amar. The question is, can I simulate an entire PCB with electronic components and mechanical housing on it to get an idea of how my antenna would perform?
The answer is a qualified yes. So the idea is you can simulate a full PCB. There is no problem. Okay. The trick is, what is your fastest signal? What's the fastest frequency? What that impacts is the size of the problem you need to solve. So if you have very high frequency and a very large board, you will still be able to solve it. It's just going to need quite a bit of computational power. So probably on your standard like 16 gig desktop or whatever, you might run into performance issues. But if your frequency is low and you want to do a full PCB, that is still, you can still get around and get that done on a typical desktop. And as an add-on, we are working on a new cloud-based version. So it's those kinds of limitations that you might have because of hardware on your desktop, you wouldn't have if you go to a cloud solution where you can actually scale up the resources. So the answer is yes, but again, it might require some additional resources if you're going high frequency, very high frequency.
Great. Thank you. I think this next question may be directed towards Adam. The question is, how long does it take for an engineer to become proficient to use HFWorks simulation tool?
Well, it all depends. I mean, if the engineer, is good at using SOLIDWORKS, I don't think it will take him a long time at all. And as I mentioned earlier, I showed that the interface, the toolbar, the documentation, all this stuff, or the menus, or everything in our HFWorks is similar to that of SOLIDWORKS. So I don't think the learning curve is long at all.
Great.
I hope that answers your question.
It's wonderful. The next question we have here, again, I think this is best directed to either Adam or Dr. Amar, but the question is, what type of antenna was used to communicate with the Mars base?
So to communicate, so there is this concept which is antenna gain, which is essentially the ability of antenna to send signals in a given direction. Okay, and this is to get gain, to make the antenna point in one direction. You need big antennas, electrically big. So if you're communicating at I don't know 1 gigahertz, for example, your wavelength is about 30 centimeters. You want an antenna that's probably at least 60 wavelengths to have a very narrow beam. Typically, the best antennas to do these are parabolic dish antennas. And if you noticed, for astronomy applications and so on, these are called telescopes. They're not even called antennas because they're really huge 64-meter dish antennas that sit on top of mountains. So there is not a lot of, they don't catch a lot of electromagnetic noise from Earth so that they can listen to very weak signals from space. So whenever we go to space, we really try to, especially for long distances, we want to be using large dish antennas.
Great. We are a little over time, but I think we'll squeeze in one or two quick more questions. Talal, I think this one is directed towards you. The question is, how do you include supplier data in the PCB design?
Okay, so again, that is a very good question. Everybody needs that. Whoever is doing PCB design, their main concern is to include the supplier data. For that, we have a very, very good built-in tool which can connect to different types of supplier like DGK and Mauser, etc., and directly take information from there. And it is built into the tool in such a way that once you start picking up your elements, resistor, capacitors, inductors, etc., it gives you options of where to purchase from. Obviously, your product could be built anywhere from, you're designing sitting in Canada, but it might be built in Taiwan and they need local suppliers, etc. So it is all over the world. It has a database of suppliers, and then you can pick those and include them in even different type of numberings, and suppliers have their own numbers, etc. So it's a sophisticated system which is built into the SOLIDWORKS PCB, considering this is a very important feature for the PCB tool. And definitely please contact us. We can show you in detail all these features about SOLIDWORKS PCB. We'll be happy to do a demonstration for you. And if you have any concerns or particular questions, we'll be able to answer those.
Perfect. Talal, this next one may be directed at you, but if any of the other presenters would like to comment, feel free to. The question is, as a beginner in PCB designing, what would you think would be the best way to learn and practice the concepts of 2D and 3D PCB creation? Courses, certifications, books. I've used Eagle before in college and wanted to know if there was any other open source tools specifically for 3D PCBs.
So Eagle is a good one, obviously, but SOLIDWORKS PCB is easy to understand. We do have a system in SOLIDWORKS where you have training courses, you have certifications, all under one umbrella. They are offered in universities as well, but of course, to any purchasing person can access the courses. They are online. You can do it on your own pace. You don't have to attend classes. So at your own pace, you go through all these courses and they teach you step by step. We have training courses. I do training for companies as well, where we can train you. Typical training is about 3 to 5 days, depending on what you want to do. All that content is provided as base for SOLIDWORKS. So SOLIDWORKS has a very comprehensive certification program as well as training program. I would definitely ask you to consult Jessica and us, definitely, and I can point you in the right direction after this webinar.
Great. And you know what, we did have one interesting question come in just now. I won't direct this at anyone in particular, but if anyone has any thoughts they'd like to share on this. The question here is, would it be a problem for the transition into 5G, as most people are unaware of the concept of it? There have been some occasions where rumors were spread about 5G emitting too much radiation, which is extremely harmful for our ecosystem and personal health. I've been taught that the sun emits more radiation, relatively harmless, in comparison to 5G. However, some people may buy into the false rumors and try to delay or refute the transition to 5G. Any thoughts from our panelists here?
Yeah, no, I think there is a lot of misinformation out there. I mean, 5G is not any more harmful than 4G or any of these other technologies. There are regulatory bodies that make sure that whatever is emitted is within specified limits. So you can't just radiate power the way you want. And that's where like software like ours helps you to figure out, are you actually respecting those power levels, those power densities? Okay, so when you put an antenna, it's gonna emit radiation around it, and you can predict how much radiation it's gonna be. And the CRTC and the FCC have rules. At a certain distance, the power has to be within a certain limit. Okay, so nobody has free reign and can do whatever they want with 5G. It's highly regulated, and those levels are safe. And I personally, I'm in this field, and I have no issues whatsoever. I think the issue of 5G is more technical. It's really having these communicate efficiently. Really, the bottleneck is really getting very good antennas, because especially to get a lot more speed, you have to go to high frequency. You have to go to 28 gigahertz. At 28 gigahertz, your antennas have to really be focused. So a lot of challenges. How do you make these next generation antennas and so on? So it really plays into this kind of some level of expertise and knowledge of electromagnetics. I think it's going to be very helpful to PCB designers and high-speed 5G designers and so on.
But of course, our product HFWorks will be able to help with that.
Yeah,
5G antenna simulation.
Great. All right, well, we are definitely over time, so I think we'll need to wrap it up here, but those were some great questions. Thank you very much to our attendees for your participation. There have been a couple of questions from people interested in learning a little bit more or getting in touch with some of our presenters afterwards. So what we'll do there, we will include the contact information in the email that you'll receive from us tomorrow, along with today's recording. So if there were additional questions or conversations that you'd like to have, we can certainly pass that information along to you so you can get in touch. Once again, thank you very much, James, Adam, Dr. Amar, Roman, and Talal for a wonderful presentation. And thank you all to all of our attendees for spending a little bit of your Thursday here with us. We hope to see you again very soon. Thank you. Bye-bye.
Thank you. It's been a pleasure. Bye-bye, everybody.
Thank you. Thank you, everyone, for your participation and contribution.
You guys, take care.
Bye.
Bye.
Thank you.